That works. Cool. Hi everybody. I'm Jay. I'm a Scala developer at JP Morgan. I've been a functional programmer for about 2.5 years now, and been a non-functional for 10 more. Over last year, we have heard a lot about something called direct style way of writing Scala code. Martin Odersky, more specifically, was a proponent of this, not only in his Lean Scala article, but also in some of the conference talks. He compared it with monadic style way of writing code. In JVM world, actually, Project Loom was released in JDK 21. For those who don't know about Project Loom, it provides the ability within JVM to run virtual threads, and you can have thousands of them. Previously, JVM only supported OS level threads, which are like resource heavy, and can only have a handful of them. So this is a very big boost to concurrency story of JVM itself. In Scala side, we have some budding libraries like SoftwareMS Aux and Gears from EPFL. They both base their design on Lean Scala principles, while also I don't know what this is, but okay. While also they basing their concurrency and execution engine on Project Loom. So the questions we need to ask are we heading towards a future with no monads? Has Project Loom thrown down a gauntlet on fiber party? Is it really all that better? But wait a minute. The questions we need to really ask are, what is direct style way of writing code anyway? Over the course of the talk, we're going to explore that. And I will share some of my observations on direct style way of writing code in Scala, and then how it looks compared to popular effect systems like Cats Effect and Theo. Since I'm like a type level programmer, I will just use Cats Effect, but the same applies even for Theo. For comparison, I'm going to pick SoftwareMS Aux, which is a fairly mature library by now. And I'm going to use Cats Effect for effect system-based library. For the course of the talk, we're going to cook tonkatsu ramen. If anyone has cooked it, you will know the pain. So essentially, tonkatsu ramen has predominantly these pieces. There's the broth, which takes about 12 hours to cook. Then there is charshu, which is braised pork, and that needs to sit in oven slow cooking for about 3 hours. And then you have some ramen noodles. You can buy instant noodles and just boil it in water. Then some mushrooms and veggies. So this example really helps in writing very good concurrent code. And then all kinds of stuff can go wrong while cooking this. And we will see how things going wrong can be handled in code by using errors and then handling them, all that stuff. Personally, I've never cooked it, but I try to. I'll try to inspire some of you guys to try the recipe for the weekend. No functional programming talk can be complete without talking about types. So let's start there. Functional programming, as one of its base tenets, likes to segregate pure and impure functions. Pure functions are ones which are predictable. You give it some data, and then you get the return value, which is just based on the data. Impure functions are not so much. It either can change observable behavior of the system outside, or it can give data back, which is indeterministic, let's say from a database query, which is an indeterministic data return. Given that's the premise, let's start with Cats Effect. I'm going to do a comparison of Cats Effect and Aux. Let's start with Cats Effect. And I try to represent cooking all of the components of tonkatsu ramen itself in all of these functions here. Broth has a function, chashu, soft boiling eggs, preparing veggies, and cooking ramen. The basic contract or the signature of each of these functions have IO, data type from Katz effect. So IO principally represents some sort of an impure operation which is happening. And in this case, its impure operation is actually you are cooking something. And IO type as a one type parameter, and that represents the data which you get back once the impure operation is complete. And in this case, whether it could be broth, chashu, and all of these. Let's look at assemble ramen bowl. Once you have everything prepared, you need to assemble it. You just put it in a bowl. But the assemble ramen bowl actually takes like the plain data types here. So that means we need to resolve all of our impure operations, get the actual data, then pass it to assemble ramen bowl. While assembling itself is again some physical activity, we will represent even that as an IO, which will give you back a ramen bowl at the end of executing it. Now, how do you run through your recipe? That's by using for comprehension, which is a syntactic sugar on flat maps. And since IO is a monad, the only way to execute IO is to run through flat maps. And for comprehension gives like a neat syntax to sequence all of the operations in the order you need. In this case, you would start with broth, you would cook chashu, veggies, soft boiled eggs, ramen. And then once you have everything, you call assemble ramen bowl with all the resolved, and then you yield the bowl back. And key thing to note is that any IO operation itself, any IO function, you have to flat map it for it to execute. It's lazy, and then if you forget something not added to your flat map chain, then it never gets executed. That's a two-sided sword, and let's see how that works out. Consider this other case where I have just two functions. One is to cook ramen in boiling water, and then soft boil eggs. And let's say you start doing ramen, and then you hear a doorbell. You're just cooking for yourself. You hear a doorbell, your friend shows up, and then you want to cook another pack of ramen for that person. So you have two different calls to the same function, and this can actually be refactored, and then you can make named value by calling cook ramen once, and you can use the same value twice. This is exactly same in behavior compared to the previous one. That means you can fearlessly refactor your operations while also maintaining your behavior in the code. So this combination of laziness and the way that you need to always flat map on IOs leads to very good refactoring abilities within the system. All of this leads really well into this architecture style within functional programming circles called functional core and imperative shell. Think of functional core as your pure functions which operate on data, and then it uses your business logic and all of that to transform data and give you back the results. So that's defined in the core, and then that can hold all of your domain logic. And then you have this thin imperative shell at the top, which will pass on the data from external things. It could be your database, it could be from your HTTP API, or it could be Kafka or anything. So that will pass in the data into the functional core, do some processing, and then pass it out. So there is like a clear boundary. You can set a clear boundary on what's pure and what's impure in your application, just by following the types. So this is like really easy to do with effect systems. But there's one pitfall. Given this being one of the positives, there's one negative thing. Let's talk about something called function coloring. It's a really great article by Bob Nystrom, What Color is Your Function? Pretty old, but still it holds very well. Consider this is a toy language he uses on the blog. And consider you can only define functions by attaching a color to it. So either you have a blue function or a red function. The analogy here is the blue functions are pure functions and red functions are impure functions. You have to choose one. And there's no middle ground. There's nothing. You choose the color of the function as you define it. And that influences how the function is executed, how it can be composed, everything. So he forces it by doing this. So if you want to execute a blue function, you have to have like a blue keyword after calling it, and then the same with red function. Now you can call blue functions from red functions, but not the other way around. If you do what's happening here, you need to turn the function here into red. That means you will have a chance of turning your entire code base into a huge IO code base. IO type can spread like with virality in your code base. You should be really careful on setting clear boundaries on what's the functional part of your code, what's the non-functional part of your code, and manage that really well. With that out, and this is where we were, IO-based functions. Now let's look at aux code. Aux does not have a logo, so I'm just using the emoji here. Looking at the same function, we got all of these components. Now these look like pure functions because there's no type which determines whether they are blocking operations or they are impure operation engineering. So we will start with signatures which are plain to look at, but they could be blocking operations. They could be writing to database, writing to HTTP API, anything. And the way we sequence it also is simple. You would sequence as statements, and they all execute one by one. Consider the cook function itself is running within a virtual thread of project. And every time there is a blocking operation, let's say prepare bot, the virtual thread itself is taken off from the CPU context until the blocking operation is complete. Once it is complete, it's brought back into CPU, and the next step is executed. And that goes on until the whole operation is complete. So there is the whole pausing thread and resuming it. It's up to the runtime itself. And then there's no for comprehensions, there's no flat maps, anything. It looks straightforward. Now let's move on to next section. We saw types. Now let's see how to handle failures in both cats and aux. There are two main aspects about writing any program which potentially can lead to errors you need to consider. One is how do you recover from those errors? And then how do you compose programs which potentially can give errors? For that, I'm going to take example of this tonkatsu broth. So tonkatsu broth itself is cooked in a simmering pot on a stove. It's got pork in it, and it's got onions in it, and a lot of other things. It takes 12 hours to cook, and then you need to constantly monitor it. So there are a lot of things which you need to monitor. We'll see what they are. Consider the monitoring happens once a hour. Once a hour, you open the pot and then see something, whether something is going wrong. You take a corrective action and then resume monitoring again later on. Let's start with cats. So there are going to be few checks which we need to do every hour. There could be a scum buildup at the top of the boiling pot in the water that needs to be removed if it is too high. Since the whole thing is boiling, you are losing water every time because it's converting into steam. So you need to check water level. If it's going too low, you need to top up with some water. So the scum level can be low, medium, high. And then let's fill out these functions, check scum and check water level. I have deliberately made it really simple. And all of these return IO unit. If everything is right, they are going to return unit. If something is wrong, let's see what happens. Let's start with checking scum level. You open the pot and see what scum level is. If it's too high, we're going to raise an error. That means that the IO, when it resolves as an error. So for that, you can use the raise error combinator. And then at the moment here, I'm using raise error actually takes any throwable. At the moment, I'm just using runtime exception. We'll see a little more advanced versions later on. I'm going to say that scum level is too high. And if it's not the case, just return I of unit. Similarly, for water level, if it's going too low, you're going to raise an error, or else you'll say it's all right. There's another thing which can go wrong is the heat of the pot itself. It could be possible that you are burning the meat, or it could be too low that it's not boiling. So I'm going to represent those error conditions as heat error, which is an ADT of two cases. One is low heat, another is high heat. And we're going to check temperature. Every time you check temperature, whether it's boiling or right, say you use a thermometer. And then if the temperature is slightly low than boiling, you say that I'm going to raise an error which says it's low heat. And if it is it's boiling too vigorously, it means you might burn the meat which is there, and you say that it's under high heat. And then if it's at perfect temperature, we don't do anything. And so we have a little more richer information here on what kind of error we have. Now that we have those components, check scum, check water level, and check temperature, let's write a function which will monitor the broth over 12 hours. So at every monitoring instance, we have to do three things. One is check scum, and if it is too high, we're going to handle it by doing a corrective action. In this case, consider your println here being like a function which will remove the scum. Similarly, for water level, we can add water if it is low. And for temperature, it's a little more nuanced because we have low heat and high heat, and based on whatever you have got, you need to take the relevant corrective action. And that's done by recover with combinator on IO. And handle error with actually catches everything. I've kept it simple, but the trap with the handle error with is you can catch any exception. So you should be very careful with using handle error with. But recover with is pretty solid. You can specifically catch valid ones. And once we have this check, we need to repeat this every hour for 12 hours. For that, let's write a simple iteration loop. And we're going to sleep 1 hour. And then we're going to sequence through all of these checks. Either we could do this as stat map, or I've used a nice little operator here to sequence all of those operations. And then once you're done with that, you have a list of IO operations. But essentially, what you need to return is an IO. So for that, we need to do fiddly bits. The fiddly bit here is a sequence call here. The sequence call takes list of IOs and turns it into IO of list, which is implemented by traversable type class. So this is our function for monitoring broth. Now, let's look at how it looks in aux code. But before that, let's look at Java code, which is for starting virtual threads. So this is verbatim from JDK code base. So you have start virtual thread as a function. It takes runnable. So runnable is a very simple interface, very pedestrian. So it's got a run function. There is no way to tell what possible errors could be, and then there's no return. Like you run something, what's the return? It's void. So very constrained. So you don't have rich type information. There's no type safety and anything. If you want to say something has failed in a runnable, you have to throw an exception. So aux tries to aux and guess probably they have their high hands tied. Can't do anything. But I have taken some liberty, and let's start with the same monitor broth example here. And we're going to see two functions. I've taken some liberty. I'm going to use either just one monad in my talk with aux. I'm taking either. Might as well replace it with the throwing an exception. I'm taking either. On left side, I'm going to show a possible error which is going to happen. On the right side, it's in unit. It's the same thing. Instead of having IO and for comprehension and all of that, it's either a left on check scum, or it's a right if it's not high. Same with water level. If it's going low, we're going to give back a left on and give a runtime exception. Now checking temperature. we're going to stick with the same ADT of error, low heat and high heat variance. And check temperature again is going to go through like checking in thermometer, temperature is low, high. We're going to give left or right. Not an interesting point is the function here, check using thermometer. There's kind of no way to tell whether it's an impure function, a blocking function, or anything. It's just a function. It looks like something. It does not have any information on what it could be. But as an execution engine itself, if it's a blocking thing, the virtual thread will just get thrown out of CPU if it blocks. Let's construct monitor broth function. Same. We need to do 12 iterations once every hour. And aux has neat little function to sleep the virtual thread, aux for sleep, which will sleep the virtual thread itself for 1 hour. And we're going to check whether we have a left or right on each of the cases, and then take corrective action. With check temperature, we have a little more information on what. This does not need sequencing as we did with Cat's effect. It has no for comprehensions. That's with handling errors. Now we're going to move to concurrency patterns. Concurrent execution of code is like you have multiple things which you need to run at the same time. That's concurrency. For that, let's cook chashu. So cooking chashu is slightly more complex, I would say. You start with pork belly and then roll it into a log, tie through the log with strings, and then sear on a high heat pan all sides until it's very brown, and then take a casserole, probably take a casserole, place your pork belly on it, and then we are going to cook that in an oven using braising liquid, like a soy-based braising liquid. And all things can go wrong with an oven. And then this has to cook over 3 hours, and you need to keep monitoring it, or else it's going to go bad. So let's see what's going to happen with that. We'll start with Cat's effect code. Let's handle errors first. I have an error ADT, chashu error, where it could be getting burnt as one of the cases. There could be too much liquid in our casserole, and then that means that your meat can turn out to be very soft and squidgy. It could be unraveling from the strings, and you need to tie them together. It could be drying out. That means you need to add a little more of the braising liquid. So while cooking in the oven, these are the possible errors which can happen. Similarly, but check with it. We're going to do another check for check chashu. That means over three hours, you need to constantly monitor your inside the oven, what's happening. And I have simulated possible errors which can happen. And for each of them, we will do raise errors on those specific subtypes of the ADT itself. Might happen anytime. If nothing happens, then we say that we don't have a error condition itself. So once we have this check chashu, we're going to write monitor chashu, similar to monitor broth. It's going to run over 3 hours. And then there's only check chashu operation. So let's start with handle error on that. So you get all of these cases, and then we need to take corrective action. If it's getting burnt, turn it around so that the less cooked side is exposed. If there is too much liquid, then let's remove some liquid. And if it's unraveling from the strings, you need to retie it and stuff. And if it's drying out, we need to add some more of the braising liquid itself. And we need to do this over 3 hours. I'm going to do something similar as monitor broth. Run through 6 iterations, sleep every 30 minutes, and check. Do this for through 3 hours, and we do the sequence again, just because we need to give back. Now, we got chashu, monitor chashu, which runs for 3 hours. Now we got the broth, which runs for 12 hours. Let's say we want both of them to complete at the same time. That means you start broth and wait for 9 hours and then start chashu so that they both complete at 12-hour mark. Let's write a function for that. Chashu and broth prep. For comparison, because we are in cat's world. What we're going to do here is concurrent execution. Previously, we had things which were just calling the function and in the for comparison. But here we're going to do dot start on the IO. What it does is it's going to take the operation monitor broth. It's going to pack it into a fiber, and then it's going to start the fiber running, and immediately the control returns back to the for comparison which is here. And then you get a handle to the fiber itself. And after that, the for comparison is going to wait for 9 hours. And we're going to do the same thing with chashu. Take monitor chashu, put it in a fiber, and start it. And the control comes back here with the fiber return, handle to the fiber return. And then we need to wait for both of them to complete. And how do you wait? I call join. It comes from thread.join, very old nomenclature for that. You do thread.join on fiber.join in this case for chashu and broth fiber. Well, actually, you could do this together, but I have kept it simple. You do join one after the other, and it's still fine. And once both have completed at 12-hour mark, you say that chashu and broth are complete. And that's how you would do concurrent execution. You have these fibers, you can run them and then wait for them to complete within CatSFX. Now let's look at aux code for the same thing. I'm gonna rush through this. We had the chashu error one, all of that. Check chashu doing the same thing. We're gonna check for problems, and then based on random occurrence of the problem, we're gonna say one of the subtypes of the chashu error itself. And if everything is all right, it's gonna say unit. Monitor chashu, same thing. Instead of IO sleep, you're using aux.sleep, and we need to do this over 3 hours. So there are 6 iterations, and check chashu, and you get all the cases, and then take corrective action. Think about these printlns as we are taking corrective actions, and there could be functions themselves which get executed. Then let's write chashu and broth prep. Previously, we need to time it so that both are ready at the same time. And this is where there is a significant departure from how CatSFX does stuff. We need to use something called aux.supervised concept. So aux.supervised takes in a block of code, and it bases its whole mechanism on something called structure concurrency. So structure concurrency comes from maybe Python, was it? I think Python was, I'm guessing Python is the one which did first. So structure concurrency is simple to understand. So the whole bit about structure concurrency is that consider you have a block of code, and then you have a bunch of threads which are running in that block of code. That block, consider in this case line 1 to line 14, and then you have like 3 or 4 threads which have spun up here within this block. All of them has to either complete or get aborted by the time the control reaches the end of the block, which is line number 14. That gives very good safety mechanism against hanging threads, unaccounted for threads, which are getting leaked out, consuming your resources. You don't know what's running, and then you have to like turn down your system to like kill all the threads. So that's a very good safety mechanism against this. And aux.supervised bases this entire thing on Project Loom structured concurrency implementation. And for that, for creating virtual threads, aux has fork, just like we had start on IO. So fork, what it does is any block of code which you give into the fork, it's going to pack that up into runnable, which we saw, the runnable type, and then runs it in a virtual thread. We're going to start the broth, and then we're going to sleep here for 9 hours. So this bit is running in a virtual thread already, and then the control comes back, and then we're going to sleep in this function, which you think as another virtual thread which is running. You got two virtual threads. One is the control thread. Another one is running broth. And you're going to do the same thing with Chashu. And then we wait for both of them to complete by calling join on both of the virtual threads. And once they are done, say that they both are ready. So this is how virtual threads can be spun up in Ox. Now, for some disappointing news, let's start with catch effect. Consider a case where you are not paying attention and your Chashu got completely burned. And that I've added another subtype into Chashu, the catastrophic burning. Consider like your fire alarms are like blaring and all that stuff. So you got the catastrophic warning that's returned as one of the cases. And in this monitored Chashu, we were able to take rectifying measures for other cases, but not for this. And we're going to propagate raise error from this point for monitored Chashu, and that will affect how the concurrent story works out. So the concurrent story here is we have Chashu and broth prep. We are expected to continue monitoring broth even if Chashu fails. We at least have broth to work out with. You can just eat ramen with this broth. That's still fine. So the way you rectify or the way you handle that is by calling attempt on join. That will turn any possible IO errors within the Chashu fiber into an either, on which you can see that what's happening, whether it's on an error condition or not, and take corrective actions. Now, if there was an error condition at Chashu fiber join, and then we didn't handle it, that means since flat maps are fail fast, the whole for comprehension is going to exit, and then you'll be left with broth fiber which has not been joined at all. So it's going to be there. It's going to be abandoned. We don't know what's going to happen with broth fiber. It may complete, may not complete. We don't know at all. So the whole control is going to exit out of for comprehension. So that's one thing which to be really careful with join here in SFX. Let's do the same thing with Ox. Stuff. The interesting thing is here. Now we passed on IO tracer at this point in, right? But we cannot do that here for two reasons. One, we need to somehow signal that monitor Chashu has failed. The only way we can signal it is by throwing an exception. That's because of this. So our monitor Chashu is actually running inside a virtual thread. Then the way we tell the virtual thread has failed in a catastrophic way is by throwing an exception. And the way you would handle it here is the join will throw an exception here, and then we need to like handle it so that our broth will continue and completes. If we don't handle the join exception from the join here, what's going to happen is the whole bit here between line 17 and line 1 will be in an exception condition. So there will be an exception thrown, which is uncaught. That means the whole block is going to exit. While it's exiting, it's going to make sure all of the threads which are spun up within the block is going to get aborted. That means the broth prep is going to get aborted, and then you won't be left with any broth at all. No consolatory phrases there. So we need to handle it here, and somehow we need to make sure join is going to still happen for the broth prep. So that's one guarantee with Oxford supervised and structured concurrency, in that no threat left behind is how the safety is guaranteed. That's with concurrence code. Let's look at resource management. Anything which is a scarce commodity within a computing system would be called resource. Scarce commodities here could be file handles, database connections, any of these. And we need to be really careful on how we manage it. It could be possible that programs crash, and if that happens, we need to make sure that the resources either get closed or reassigned or any of these things. So let's look at CATS code for that. So the resources we use here are stub and one, essentially. Now, while your charge is getting completely burned, you see that your fire alarm is blaring. The first thing you should do is like turn off the one. And that's ensured by the resource constructs within CATS. This resource is the type which is used to manage resources. And it takes 2 blocks of code. One is how do you acquire a resource, and then how do you release a resource. Here is some code for how it would look for stove, similarly for oven. And then how do we use it within our context? Pretty simple. You call use on it. And the guarantees which you get out of this is, so the use starts here and then it ends here. And since there are like two resources, you can do a tuple so that you get both of them together, all that neat little things from CATS. And the guarantee is that no matter what happens with charge and broth practice, whether it aborts, whether it completes properly, anything can happen. It can throw an exception, crash and burn. There's a guarantee that both stove and oven are safely closed at end of this block. And that leads to no leaked resources. Let's look at aux code for the same. Aux needs you to use supervised. So it not only helps you do structure concurrency, but also they have made in a way that your resources are handled well within supervised block. Similar to CATS resource, they have use in scope as a function to construct resources. And similarly, it takes 2 blocks of one to acquire a resource and one to release it. We're going to acquire stub on the one. And then the using is just slot in your acquisition within the supervised block here. And no matter what happens with the threads which are getting created here, or whether they join, or whether while they're joining, they're raising exception or anything, aux and project Argo will make sure that the resources are closed when the code exits here at the line number 20 block. That's with resources. And finally, one last thing we can have a look is testing. Now, problem with our code is it takes 12 hours to execute. Now, if you want to run your unit tests in milliseconds, that's a little hard. So let's see what we have in store to do that. With CATS effect, they have a concept of mock time. And at the moment here, I'm using CATS effect Scala test integration. And that gives something called async IO spec and async word spec. So well, within the spec here, you actually just can call the function and then pass in like stove and one, let's say. Even though this takes in real world, they are like pauses, everything, which essentially takes 12 hours to run. The mock time, execution runtime, which is by something called test control within CATS effect, will make sure that this will run within milliseconds, even though it has so many steps involved. And it's within for comprehension. And if it completes, that means the for comprehension completes without raising an error. You're going to use succeed from assertions, Scala assertions, to say that it's all good. And we're going to just see whether it actually completed or not. And that's all you need to do to write tests against highly concurrent code in CATS effect. Unfortunately, in aux, it's not the case. It seems it's not possible to mock time. within virtual threads. It's because underlying project Loom has no way to mock time within virtual threads. So it's still an open issue in Ox GitHub. And Adam Wasky has said that unless Project Loom provides some ability to do that, they cannot support at the moment. So that was my comparison. I try to be as unbiased as possible. And I do not think I can walk out of here if I do some sort of, hey, this is something which you need to use alive, actually. So here is the reckoner. Hope you guys had, if you guys never looked at direct style code, hope you guys have some exposure now. Thanks for listening. If it was some inspiration to cook tonkatsu ramen, please do give it a try. I used, if you guys know Andy Weissman, the popular YouTube creator of all the cooking things. So I used his YouTube video as inspiration for the whole bit. Okay. Thank you, guys. Thanks for listening. I can take any questions you guys have.
Yeah, thank you for the presentation. Very hungry now. So if you have a something I couldn't quite follow is that if you have a box supervised block,
yeah,
and you have a uncaught exception, say when you're raising the port, and you're still waiting on the broth to complete, will that automatically cancel the?
Yes, it cancels any of the virtual threads which are running in the block.
And how does that look like in cats then? You'd have
to
recover and do it manually. You kind of cancel the other one.
You have to recover, or else it will. It will not stop the fiber itself. So consider you have two fibers, and one of them raises and you.
The first one fails,
the fork comprehension is not exit, because it's failed path. But the join on the other one is never executed because the fork comprehension is executed. But the fiber is running somewhere because no one has told it to stop or anything. So there's something called fiber leakage as one of the pitfalls of not handling your exception from fiber.
So you have to in your code and then explicitly mention the other fiber or all the other fibers and say cancel.
Yeah. You had since you have the handles to all the fibers, you can cancel, or you can handle the error and wait for the other ones to complete.
So that makes sense. Thank you.
Just a note to that. So if you wrap the fiber into a resource,
yes,
it gets released automatically.
Yes, that's another way. Yes.
Yeah,
if it's in a resource, if there is a connection with other ones, this will get cancelled. Won't be jangled fiber.
I'm in the middle. Not really a question, but have you seen Cats Effect CPS, which is like a halfway point through from Cats Effect?
Okay.
Ox.
No, I have not. Sorry.
Yeah, CPS does just macro transformation, allowing you to like pull a weight.
Is it the continuation passing style?
Yeah. It's basically based on the DOTI async CPS sort of thing, which allows you to keep the guarantees from Cats Effect and the APIs, but still use like a weight.
Oh yeah. Okay.
The direct style.
Thank you.
Sorry. Yeah. So I just want to go back to the previous conversation about like fibers and stuff.
Yeah.
So typically, I think they do recommend against using start, the starting fibers using start because of exactly the
okay.
You mentioned. So I just want to mention that there are a lot of combinators to help you run things in parallel, and that will handle these cases.
Yeah.
Like
power map and
power traverse, right? That sort of thing. The provider as well. Haven't used it myself.
Thanks for the talk. Question about direct style as it's used by Ox, possibly
Yeah.
in how it's used by Gears.
Yes.
So Ox's version of direct style doesn't use context functions or anything, which I think are the Scala language features you'd expect.
Sure. Yeah.
So I feel if it did, you probably would be able to mock in the timer as a context we're running in. That would solve that problem there. I don't know if you have anything you can say about how Ox and Gears compare, or
No, I didn't look at Gears. So what I think the messaging of Gears was that it was more focused on Scala native than writing general programs as such.
Gotcha.
But there's, yeah, I didn't look at it. But I think in a sense, I think Gears is using a little more of Scala 3 cutting edge features like capabilities and all of that. Right, Ox uses one capability, which is the Ox itself, but they're not using anything more than that. Probably they're just still waiting for the capabilities to be a little more mature in Scala 3.
Thanks.
Guessing that's the.
Thanks for the talk. Well, maybe I'm biased using flat maps more as an everything. And like, it looks simpler to use, but like, how do I know if it's like synchronous, pure asynchronous?
Yes.
What's happening underneath? Looks easier, but then it becomes almost like Java, like,
yeah.
Bro, should I wrap it and try?
Sure, yeah.
Maybe with the capabilities and checked exceptions, that would be better, but now it's just like, it's like Java in a way.
Well, probably that's why now the Scala ecosystem uses check exception, because it's a flawed mechanism. Like, you can say that this function or this program can throw checked exception, but no one is stopping you from throwing runtime exceptions, which are like not there at all in your function signature. So it's like a little bit flawed. That I think that's why Scala never does check exceptions.
But wasn't there like a SIP with the like check exceptions using type classes?
Yeah.
So do you have any recommendations, like any ways to tell, like, is it safe, pure? Or like, I shouldn't care in the first place, and it should.
Well, there is within Ox, you can have a function which can use a capability. You can say that it's using Ox. If you don't know what capability is, like an implicit parameter, say that def this function using Ox. That kind of shows this is a blocking function out of that. Well, that allows you to use things like fork outside of supervised block. At the moment, within Ox, if you want to use supervised block, using scope, any of these things, fork and using scope, you should be within supervised block. So one way to not do that is using Ox capability. So that will allow you to use fork and using scope outside of the block step, and then you can just call those functions. That's the only thing which I've seen. Maybe they have plans as the time goes.
Thank you.
Myself, that's all right. So when let's say that I'm writing some code with Ox and I'm using this supervised block, but I forget to call join, what actually happens to my my thread?
I don't know.
You need to run an experiment after this then.
Yeah, probably it'll kill all of them because you're not waiting for them to complete, and then the program control itself will end there. So you have these threads, but you are not waited for it. Immediately you end the queue there. It might.
Well, thank you very much.
Thanks.
That was incredibly insightful. For people who are on the Zoom call, I appreciate that we haven't asked any of your questions. I'm sorry about that, but